Thank you for introduction. So my name is Marko Šimić. I'm coming from Croatia, University of Zagreb. And my area of research is related to the development of technology for landmine detection. So let's start with the problem and motivation for my research. So anti-personnel landmines are explosive devices first used in American Civil War in 19th century. In the early stage, they were produced with metallic casing, as such being easily detected with metal detectors. But as of second half of 20th century, plastic casing has replaced metallic casing, leaving them with very small metallic parts within. And as a result, modern metal detectors now must feature very high sensitivity to, and they achieve high detection rate, but this comes with the cost of low specificity, meaning that they are not able to discriminate between different between harmless metallic clutter, which is found on the field, and metallic parts of a landmine. This makes the process very slow, expensive, and in extreme cases ends with an accident. So this from here comes motivation for development of a metal detector with identification capabilities. Here's the example of the mining procedure. So the mining procedure starts with separation of mine contaminated area into lanes, typically 1 meter wide, and then the miner cuts the vegetation, proceeding with the search pattern through the lane. So search pattern, he's following search pattern with metal detector, and when he detects something, he puts plastic or wooden marker, non-metallic marker, in front of him, and then he proceeds with pinpointing the exact source of the target. At this point, he's not aware whether the target is dangerous or not. This is problematic because each time he detects something, he must excavate it very slowly, and this gives a clue how this process is stressful, and accumulated stress can make the miner careless, and most of the accidents are caused by because of this, because the miner makes some mistakes during the excavation. So here is the flowchart of developed classification strategies. So basically we use metal detector data paired with coil pose data during the scanning to make decision whether the object is dangerous or not. The true power of this algorithm is it is exclusively trained on simulations. So we don't need to make measurements to collect the data, to train the model. This is very important from the practical perspective. I'll talk about each part of this solution in the following slides. So let's say something about the features that are used. So metal detector generates time-varying magnetic field, which passing through metallic object reacts with it and create a secondary field, which is detected by metal detector. If a metallic object is small enough or far enough from the sensor, the magnetic field passing through it is homogeneous within the object volume. In that case, we can replace this metallic object with small magnetic dipole and use this formula to express the response of metal detector. In this formula, we have HDX, HIREX, which is magnetic field and is purely depends on purely geometrical terms. Geometry of metal detector, search head, and the relative pose between the metal detector and the object. So magnetic field is scaled by the current running through it. And M is magnetic polarizability tensor. It contains object intrinsic features and extrinsic parameters, which are spatial orientation of the object. Intrinsic features, we can think of them like object sensitivity in X to primary magnetic field in X, Y, and Z direction. Here's the example of the features in time domain for PMA to landmine fuse. So since the object is axisymmetric, we have the features, two of them, X and Y axis are overlapped. And for different objects having different material, size, and shape properties, these temporal features will be different. So based on this, we make a decision. What is the object? So now I'll tell something about the measurements. So metal detector is swept over the object for a period of 60 seconds, during which electromagnetic tracking system is used to track the search head. So we acquire metal detector and coil pose data synchronously during the measurement. And using this data, we find a solution to this objective function, and from which we get the magnetic polarizability tensor and object location. Magnetic polarizability tensor M contains object intrinsic features based on which we make classification. So using MATLAB implementation, average time to find solution is about 3 seconds. So let's say something of how the training dataset is generated. So to generate training dataset, we start by MPT, so simulation of the features in frequency domain. For this, we use MPT calculator software, which is developed recently by the university, by some researcher from University of Manchester. The advantage is the simulation is relatively quick, and it can simulate the objects having arbitrary shapes. And once we simulate the object in frequency domain, as we are working in time domain, we need to transform it. So to do so, we do 3 steps. First step is a representation of these features in terms of discrete spectrum of relaxation frequencies. This model has theoretical background, and is another thing is convenient to, because it allows us table-based transform from frequency to time domain. So which is the next step. However, at this point, we didn't take into account the finite width of the transmitter pulse. So width of transmitter pulse, transmitting current running through the coil, have some width which affects the amplitudes of extracted features. So to account for that, we must multiply it by this factor. And here is the example for aluminum ball. So if we simulate with the step waveform, and on the other hand, with the width, I think this is something like 50 microseconds, we have the reduction of the amplitude. So we must account for that. And this is the last step of generating the features. Once we simulated the features for the object, we can calculate features for the object of the same shape by different sizes and or electrical conductivity simply by scaling the results. This is convenient because we can easily augment the data. And it's left to say something about the model that we use. So classification is done using 1D convolutional neural network. So CNN is employed to extract temporal features from the eigenvalues. And this is followed by two-layer feed-forward neural network, which makes a decision with some probability about the object. The data set of 100 samples, so 100 samples per class, was used for training, and 175 samples for validation. This is 25%. And as I said, we first simulate features on one object. Then we can augment the data using the scaling procedure. So we augment the data within 2.5% of the object's conductivity. We can also do that for the object size. Hyperparameter tuning is done using Bayesian optimization approach. Experimental setup. Here's the experimental setup that we use. So metal detector is swept over the scanning area, and we put the object at the depth of 5 centimeters. And this is a tracking system that tracks the search head during the motions. Test objects that we used include objects of different shapes, size, and material properties. All are non-magnetic objects. We did 70, in total 70 experiments, so 10 experiments per object. Here are classification results. Due to the high-step nature of the training procedure, we collect performance over 10 consecutive runs. So it's important to mention that the most important requirement for the model is to achieve as closer to 0 false negatives, because false negative, if the mine is confused for clutter, this poses the most dangerous scenario for the miner. As we can see, there are 0 false negatives in this table. So only misclassified object is aluminum ball, which is misclassified for PMA2 landmine. This is not surprising because they have the same material and very similar shape. So the most similarities in terms of MPT features. So, but in the end, overall accuracy of 98% is quite encouraging. So that's all from me. If you have any questions, please ask.